Hi students, welcome back to the online lecture series on VLSI testing and design for testability. The last lecture we saw the introduction of testing of analog ICs and the difference between analog and digital ICs, analog and digital signals, and challenges and the differences between analog ICs and digital ICs, and what are the challenges in testing these types of ICs. In this lecture, we are going to see about analog defect mechanisms and the fault models. What is a defect mechanism? Defect mechanism is used to define the type of defects or imperfections or the faults that may occur in a device. So they are simply used to categorize the different types of imperfections or non-ideal working in an IC. For analog ICs, we have two different types of defects or faults. First thing, it is called as material defects. Material defects, these are physical in nature and they are predominantly linked to the manufacturing or the fabrication process. For example, when you apply a dielectric layer are mostly brittle in nature. So for even if there is a small thermal stress, for example, if you are using an ion implantation or etching process, it causes any thermal stress in the nearby layers due to different nature of expanding due to temperature. One material expands to a particular extent and another type of layer it can expand more than the other. So if there is two different layers that expand differently for the same temperature, it may lead to some sort of crack in its lattice or a crystal structure. Next is crystal imperfection. So in a silicon based structure, the silicon crystal lattice is very important. If the lattice structure is imperfect, it creates a impedance mismatch. Whenever there is a crystal imperfection, that particular place, it poses a higher resistance to the movement of electron than the normal crystal structure. The next one is surface impurities. So whenever if we go for different layers, when you apply layer upon layer for building ICs, if there is any surface impurities or difference in diffusion of ions, this concentration, it creates some problem. So that is the cause for surface impurities. Next is ion migration. Ion migration is, for example, you may have initially in fabrication when you are fabricating an IC, initially you would have gone for n plus layer, but after manufacturing of that particular IC, it goes to a consumer and he starts to use the particular device for more than 10 years. So after 10 years, what happens is, due to the movement of electrons inside the particular device or inside a transistor, the concentration of the ions within the particular material, for example, consider a source. The source part, the number of electrons, it changes with respect to time. So after 10 years, it will not be same as it was manufactured. So this is because the ions migrate over time towards the drain. So this is one more material defect. The second type of defect mechanisms identified is processing faults. So processing faults, there are various types of processing faults: oxide thickness, mobility change, impurity density, diffusion depth, dielectric constant, metal sheet resistance, missing contact, and dust. These are majorly for name suggests these are different imperfections in the procedure that is being followed for creating an IC. For example, now we have reached a 3 nanometer IC. At 3 nanometer, we cannot etch each and every part of the design as it is in the file into the physical layout. There will be a change from the blueprint to the actual rendering of the IC. So this is called as processing fault. For example, the oxide thickness, SiO2 layer thickness, it can be somewhat greater than that of the actual design. Similarly, the mobility change, each of these changes from the actual design that you have on the IC to that of the actual IC that is being fabricated in the fab. Next, time dependent failures. Time dependent failures are as it changes with respect to time. Dielectric breakdown. Dielectric breakdown is the if you have a dielectric, for example an SiO2, this layer can erode over time. It may be due to the temperature within the IC. So as you already know, when an IC operates, there will be lot of temperature islands that are created within the submodules. Whenever a particular submodules works at a higher frequency or a higher speed than that of the nearby modules, that particular high speed module, it accumulates more heat than that of the other modules. So what happens is the dielectric layer in this particular module, it uh, it uh, it goes through a higher temperature stress. So due to the higher temperature, the dielectric layer may break down over time. Similarly, electron migration. So if you see for an particular IC, you have lot of lines, power lines or a signal lines. So the current passes through these lines. So how will you define current? The current is movement of electrons under potential difference from one end to the other end. The electrons, they do not travel smoothly within the particular channel. There will be lot of collisions between the electrons and the material. So whenever the electron collides with the nearby materials or another electrons, it erodes the particular metal layer. For example, if you are having a copper line at say 20 nanometer in width, after 10 years this 20 nanometer width it may change to 15 nanometer, because the copper atoms or the copper material that creates the particular line, it erodes over time because of the electrons. So the actual wire width, it changes from 20 nanometer to 15 nanometer. So what happens? It changes the resistance of the line. Since large number of electrons need to move through a smaller width, so it creates more amount of resistance than the ideal resistance. So these are the examples for time dependent failures. Next is packaging failures. Packaging failures are created when the IC there is any shortcomings in the packaging part of the IC. First is contact degradation. Contact degradation, there is different types of contacts for the ICs. Say you have surface mount, you have dual line package, etc. So depending upon the contact which you are using, the contact wires that connect the lead within the IC to the external world. If the contact wire it becomes degraded with due to environmental parameters, due to heat or cold or corrosive atmosphere or very high temperature of atmosphere, for example in satellite applications. So at that time the contact degradation happens. The next is seal leakage. So you will have a epoxy seal over the total IC. That is the epoxy seal is primarily for isolating the total IC from the environmental disturbances. When there is a seal leakage, the environmental disturbance it will affect the working of the IC. So these are example of package failures. So as I told you before in the last lecture, there is no agreed single fault model for analog ICs. So we have a generic broadly defined analog fault model. Here in analog fault model we have two different types of faults. One is called as hard fault and the second one is soft fault. We can look at this in detail now. First one is defects. So what are the types of defects that happen? Extra defects. Extra defects are caused due to the extra amount of material. So we can see this roughly as a different as a type of DRC mismatch. Okay, so extra defect means for example in this case we are defining an extra amount of material overlap between two different layers. The second one is in etching defects. We have mentioned here during etching a particular layer can be taken out completely. Okay, other sources may be dust or due to lithography. Next, going back to the fault models, there are basically four different types of hard fault models. One is open, second is short, missing device and extra device. So let me explain each and every one of it. Open fault. So open fault is when there is a discontinuity between the lines. Okay, so if there is a discontinuity between these two lines, what this particular signal does not the signal from this FET it will not reach this point at any time, so it becomes a open fault. This is an example of short fault. In this short fault there is a low resistance path that is created between these two lines, so it becomes a short fault. Missing device. Missing device means this is a FET, so here there should be a FET here, so due to some process failures this FET can be removed due to extra etching. Next is extra devices. These are more or less like a parasitic devices that may unintentionally created during the fabrication process. So these are the four different types of analog hard faults. So what is the result or what is the effect of these hard faults? The first one is very catastrophic error. Catastrophic error in the sense this particular module if you have a hard fault, this particular module can make the entire submodule not useful for the particular application. It cannot be corrected ever. Okay, these types of errors, they create a module malfunction. If you have different types of modules, if there is a hard fault within a particular single module, the total module itself creates a wrong output, or the total module malfunctions. So other systems, subsystems that are dependent upon on this submodule for some kind of signal, they cannot work. So as a result, what happens, the total system or the total IC becomes a failure. This is one of the this is the major drawback of hard fault. So this is very very important that we need to remove the hard faults from the analog ICs. Next is soft fault. So faults, these are the faults that are acceptable to a particular level. Okay, they do not create any catastrophic faults, but reduce the effectiveness or the reliability of the IC to a particular level. For example, we have a WL ratio for each and every transistor. Due to lithography problems, there may be a change in length and width of the transistor, that is called as the parametric faults. The next is deviation faults. The deviation faults means, for example, a particular submodule should work in a particular frequency. The actual intended frequency is 10 megahertz, but actually this particular module can work only for 5 megahertz. This is because there may be some kind of distortion or attenuation that happens within the clock distribution path. So what happens is, the intended gain can be at 10,000, but what we actually receive is only 2,000. So what happens is, the reliability of the IC reduces. So what is the reason for these soft fault? These soft faults are created by the process failures. The procedures that we use for creating an IC, they will not be 100% correct. There may, due to some changes in the procedures, the intended IC can come out with different parameters. So these are called as the soft faults. So what are the fault model mapping, and what is the level, or what is the importance that we need to give to each one of them? We have three different levels. So starting from the basic level, layout level, we have extra defects and etching defects, and after that we have circuit level, that is parametric faults, and at the functional level we have deviation faults. Okay, so in this we have to work from bottom up. So whenever you address the problem at the lower level, we can reduce the amount of faults that are being introduced at the higher levels. Okay, I hope you would have understood the analog fault models. Okay, so in the next class we will be going through the analog fault models and how you are going to model the faults, and what are the various analog testing approaches in analog ICs. Okay, thank you guys.